So this is something called the Gram-Schmidt process. And quick historical disclaimer, it really should be called the Gram process. Schmidt was a Nazi sympathizer who did not actually contribute to this theory at all. So, fuck it. If you look this up on the internet, it's going to be called the Gram-Schmidt process. I'm not actually sure what it is that Schmidt is supposed to have contributed to this. No one seems to know. It really is kind of actually due to Gram and maybe another dude, but somehow Schmidt got his name on this. Whatever. Okay. So, the Gram-Schmidt process takes a set of vectors a1 through an, which are linearly independent, and turns it into a set of vectors q1 through qn that are orthonormal. And this is one of those processes that mathematicians will say, well, yeah, given a set of given a set of linearly independent vectors, I will from this set of vectors conjure a orthonormal set instead. Because you can always execute the Gram-Schmidt process. And engineers say, dude, that thing's really annoying to use. And I'm sorry for that. But as a mathematician, I love the fact that I could always take a set of linearly independent vectors and go, yeah, actually, I'd really like it if they were orthonormal, so kabam, let them be orthonormal. As an engineer, you're like, eh. So here's how you do it. Start with your vector a1. Okay. Is a1 orthogonal to all the vectors I have picked thus far? How many vectors have I picked thus far? One. Where?
One.
The one you wrote down. Yeah.
But this is the first one I'm dealing with. How many other vectors have I picked so far? Other vectors.
Oh,
0.
0, right? There are no other vectors that I've picked so far. So this thing may as well be perpendicular to everything I've got so far. It's good with that? So I can start with this one. Is it normal? So I'm going to be like, ortho, check. Normal. Eh? Like I don't know it's normal, right?
Yeah.
It's already ortho, so we're good with that. So I just need to make it normal. How do you make this vector unit length?
Divide or multiply by 1 over your magnitude.
Good, perfect. Multiply it by 1 over its magnitude, right? Just divide by how long it is. Okay, so I'm going to take a1, and my Gram-Schmidt process is make it ortho, make it normal. It's already ortho, so I'm going to make it normal. That means I'm going to let q1 be a1 divided by the magnitude of a1. Oops. Guys good with that? Okay. Now things get real. We're going to start with a2. Okay. Maybe I'll draw a motivating picture over here. I started with a1, right? And I made it unit long. So that's me going like, kabam, q1. Is with me on that? Okay, now, and this is where things are going to start to get rough. I have a vector that looks like this. This is maybe a2. Is with me? How do I know it doesn't point along the same direction? Yeah, good. So I don't get to use perpendicularity yet. I'm trying to achieve perpendicularity. So I have to use linear independence. So I know that it's not a scalar multiple of the one that came before it because it was because the set was linearly independent to start with. Is with me? Okay. now what? I need a perpendicular, right? So I'm going to get perpendicular before I get normal. Where am I going to get the part of A2 that's perpendicular to Q1?
Would we project it onto A2?
A1. So it would be A2 minus Q
Q parallel?
Yeah, Q parallel. Or A parallel.
Good.
Or,
Yep, so I need the perpendicular
Yeah.
component, right? So what I'm going to do is I'm going to project this thing in, which I suppose I need yet another color for. So we're going to project in, right? I'm going to get this blue vector here. That's going to be A2 parallel, right? And I'm essentially going to discard that thing. You guys with me? That's going to give me this other vector here, A2 perpendicular. Okay, so how do I do that? Do you remember how to project on the lines? Yeah, so I hope you're just scrolling backwards looking for a formula, right? Okay, so I'm going to turn A2 into A2 perpendicular, right? And I happen to have here a formula for A2 perpendicular. And very carefully I'm going to copy it, because if you don't, you screw it up. So A2 perpendicular is going to be A2 minus Q1 dotted with A2 divided by Q1 dotted with Q1 times Q1. You guys with me? Okay, so I've got that. Oh. You guys see something that I can exploit here?
Oh, Q1 gone, Q1's just 1.
Yeah.
Yeah.
You guys see that? So I know that Q1 is normal because I made it that way. Right, so I know that I'm going to be able to discard that part. Is this with me? So I'm going to be able to say that, so this is A2 minus Q1 dotted with A2 times Q1. This part's a scalar, that part's a vector, right? Is on board? Okay, now what? So that's, which part did I just check off? That's A2 perpendicular, right?
oh, you,
Yeah.
So this whole business is me checking off ortho. Check now, right? So now I need to check off normal. So how are you going to check off normal? This got really symbol heavy really fast, right? This is why I said that engineers hate this process, because it sucks to do.
If I just normalize it, you have to do it.
Yeah, we just need to normalize what we just got, right? Unfortunately, that's a buttload of symbols, but it's not very hard. So I take the vector I just got. So I've got A2 minus Q1 dotted with A2 Q1. And I need to divide that by the magnitude of that exact same thing. And this is what I'm going to call Q2. Goes with me? Okay. Now, what are you gonna do with the third one? Gross.
Find
Right?
a calculator online.
Yeah, find a calculator online. Perfect. Just cram this into Wolfram Alpha, let it rip. Because this is absolutely a process for a calculator, not for a human being, right? I don't want you to ever do this by hand for more than a couple of vectors. So, what's my next step going to be? I'm going to take A3, right?
And then once you have to project it onto the, both A1 and A2, there's some space that you have to make that matrix out of.
Yeah, and I can get away with something just a little bit easier because I know they're perpendicular, right? So after I normalize here, right, that's going to give me Q2, which is going to be just a tit shorter, right? In this case, I drew it so it was almost a unit vector when I projected it. Might be just a tiny bit different in size. And then because I know that Q1 and Q2 are perpendicular, I can subtract each of the projections. That's a little bit that projection thing we just did a second ago. So I know I can just project on each piece and keep subtracting. So what we're going to do is we're going to make A3 perpendicular, right? Which is going to really be A3 minus the projection onto Q1 minus the projection onto Q2. And then I'm going to have to divide by that whole mess, right? Equals mass, right? Don't divide yet. So that's the ortho part. And then the next part, we're going to make Q3, which is going to be A3 perpendicular divided by the magnitude of A3 perpendicular. Is with me on that? And I suppose vector hats all around. Where are you going to get the next one?
Calculator.
Same process. How do you know this process is going to continue to work? They were linearly independent, right? So if I could make projections onto each of these that would somehow zero out, that one would be a linear combination of the ones that came before it, and I would know I didn't have linearly independent set. So this must continue. You have to be able to continue this process. You guys good with this? You could write this out in a slightly slick way by making Q matrices out of kind of appending all of your Q's together. I wouldn't recommend that unless you're programming it into a computer. It is quite a bit easier for the human mind to grasp I project it onto the first thing, and subtract that, and project it onto the next thing, and subtract that, and project it onto the next thing, and subtract that. That said, don't do this in your human mind, use a computer. Cool. There are a number of Gram-Schmidt calculators on the internet, and you should pick one and use it. Good?